Okay, so I think we can start first we will start with like a brief summary of what we learned yesterday, and later we will see the solution to the exercise. Okay, so yesterday what we learned is that, well, we learned a little bit about the GPUs, and we learned that the memory of the host and the memory of the GPU or device uh, are in the different locations. This is not true with the newer GPUs where the memory is shared between a host and the device, but you may find that yeah, GPUs like the ones that are available on ARCHER2 or in other facilities, supercomputers, they have different regions of memory. So for those GPUs, the data can be copied from host to device and vice versa. Kernels, we learned the concept of kernels that are functions that normally execute for loops, are executing the GPUs using data that is on the device memory. And a concept that is tricky to, let's say, explain, but I will go through it again, is a memory coalescence. The idea of memory coalescence is that the access to the memory needs to be consecutive, in the sense that you cannot access, it's not performant to access one address in memory and then do a big jump and access another location in memory that is far away from the previous location. So if you access consecutive memory locations, it will improve coalescence, caching. This concept is, let's say, easy, or is for CPUs, but for GPUs it changed. I will go through it again. I create a set of slides. Please, if you don't understand that, let me know and I will go through it again. This is very important that you understand this concept. So normally what we do on the CPU, or what is the, let's say, the normal is if let me see if I have a, yeah, I think I have a pointer here. I guess that you can see the mouse pointer. So normally we have this for loop, and what we do normally in sequential, when we have a thread on the CPU, is we set for each thread, I take one of the rows with I, and then I iterate through the columns. So first I read like A00, then A01, A02, A03. So I do consecutive access to the memory. Thing here is that on the GPU, the execution, the thread execution is let's say different. We have the concept of a warp wavefront, that warps are executed at once. So let's say that we have 4 threads. So the first element of thread 0, thread 1, thread 2, and thread 3 are executed at the same time as a unit. Later, the second element is executed at once for each thread. So the execution is in that way. If the execution is in that way, when we perform that for loop, you see that this is our matrix here representing 2D, but normally memory is represented like with a line, so it's not it's represented in one dimension. And normally this is the distribution of memory of this 2D matrix in memory. So we have the element 0, 0, 0, 1, 0, 2, 0, 3, and then we jump to 1, 1, 0, 1, 1, 1, 2, 1, 3. So if we perform this for loop, that this will make sense for CPU or for a thread, P threads, OpenMP, etc. On the CPU, this makes sense, but when we execute that on the GPU, you will see that in the first execution, the first cycle, let's see, the first warp will get access to this position in memory. So the position 0, 0, 1, 0, 2, 0, 3, 0, because the threads on the X axis will be executed in parallel. I'm not sure if that makes sense or not. So in this example, we have 4 threads, 0, 1, 2, 3, with different colors, and takes, let's say, the first cycle takes the first element of each vector. So you will see that the access is not consecutive, so it's uncoalescence. If we move to this example, the thing is here, rather than iterating G, what we iterate is with the first component of the matrix with I. So you see that when, for instance, if you run that on a CPU, it will, let's say, break the caching, but on the GPU, it will be the right approach. Because again, for the for loop, each iteration in the for loop for each thread is executed at once. So this is the concept that you will need to understand for GPU programming or for parallelization on a GPU. Is that more clear? Any questions regarding this? Yeah, it takes a while. Actually, I was trying to how to say, because to figure out with the key here is that we normally think, like, let's say in the CPU you get one row, and this row is executed like in one after the other for each thread, and each thread has a row, and that's fine. But the problem is no problem. GPU is different. GPU is that the threads are each iteration of the thread is executed at the same time as the others, like in the same warp, in the same cycle. So there you need to be careful with the memory access. Anyway, I will share these slides in case that, and that is the article that I shared yesterday. I will share it again. Here is well explained as well the memory, the access memory when it's a multi-dimensional array. Okay, so in that case, I will share my screen. Let's see. And we will solve the exercise together. This should be okay. Let me. Yeah, I see that question in the chat. That's the key, that we have let's say on the CPU we have 4 threads. Each thread takes a row on the of the matrix and performs the operations, and that's it. Let's see that the threads are independent in that sense. On the GPU, threads are synchronized, or the execution of the threads are synchronized. So let's say the first iteration of the for loop for thread 0, 1, 2, and 3 takes place at the same time. So in that case, we need to rethink how the memory is accessed. Yeah, that is in the GPU, there is like some sort of a thread synchronization when this is executed, but on the CPU, you can, for instance, thread 0 are independent, let's say. So yeah, that's the point, that the threads in the GPU are independent, and the threads on the GPU are executing lockstep, as you said. So yeah, that's the, let's say, the key of the GPU execution. Okay, so I will share my window. Must be this one. So this is the, I think that must be like a, make this, yeah, should be like a big enough. So I'm here, I'm in my work directory, and I will open the file. So the idea of this exercise is to I have this operation here that I have a matrix, and I want to add for each element of the matrix alpha multiplied by one position of vector x and the other position of vector y. The matrix in our code is stored as a 1D vector, and you see that my kernel is empty. So if we go to the docs that are here, I will share the link in the chat. Actually, probably it's easier to give me a moment that I copy this here, and I have this. Okay, I have this window here. Yeah, section 2, 3. Let me see if I can. No, I need to stop sharing. Well, also another concept that I mentioned yesterday that I forgot to say, the occupancy, that we should have like a big number of threads. Actually, because of the same concept that the threads are executed like we have a lot of GPU cores, and because the threads are executing lockstep, we will need like a big number to provide enough, let's say, food for the GPUs, enough work. So this is the exercise, and this exercise, what we will do is we will use a ARCHER2 that we'll see that on the when we submit the job, and we get the time in nanoseconds. Also, is execute the keep memset. This is quite useful. Actually, this function exists in C. Well, it's called a memset. That is you initialize all of the elements of an array at once. You don't need a for loop to initialize that. So it's more efficient. So the kernel that the simple one that we will implement is this. So what I will do is I will copy this. This will be a sequential, well, a kernel that will execute in the GPU. But notice that here only one thread will do the whole operation, and the other threads will not do anything. So you will see that the performance will be quite bad. But yeah, in each iteration we will remove the while loop, the I loop, the J loop, and work with the 2D and also check if the coalescence is right or not. Yeah, so let's start. Here, what I will do is I will paste. Yeah, I will paste this. Let's see. I will fix the indentation. So I close this. I close. Okay, the indentation here is not. I can keep every chunk, or I can get rid of it. So it's fine. Okay, so this is the first version of my kernel. So you see that, as I said, one thread will do the whole the whole operation. Oh, sorry. Thank you. I forgot to. Well, actually, what you have missed is like me trying to make the code more beautiful. Let's say that. But yeah, thank you. I was what I did is I copied from GitHub to here. I copied the content of this kernel, and I was like fixing the indentation. So only the thread ID 0 will perform the whole matrix operation. And what I will do is I will execute this. I don't need to modify anything else at the moment. So if I save and I compile with the make, now here if I go submit, and I will use minus stats that gives you like a the time that the kernel will in the if we go to the git restore, you will find that you're using sys_trace. So this will give you like a more files, more information, but for our exercise we will not need that much information. So I will edit that and I will use stats. Also, if you go to rockprof, I was checking before the documentation. I will copy that in the chat. There you will find the options that you can use for rockprof. But for this, I will use stats. That's the... Okay, so save, sparse, submit. Let's see. Yeah, it's getting ready to start. Oh, done. So if I do ls, I find a bunch of I have a results CSV, database, JSON, stats. I have like several files that start with the result. So all of these files have been executed as part of a rock. Sorry, has been generated as part of a rock prof. The one that I'm interested in this is results.stats.csv. If I print that one, you will see that my kernel, the execution time in nanoseconds was this one. Actually, we'll copy that file and I will save that. Also, I will check. No, which one is this? 27. I check that, yeah, number of rows, number of columns is, yeah, it's correct. So what I will do is I will create a file called performance. And copy the, this will be serial, well, serial, yeah. And this is the number of nanoseconds that took to execute the software. I will save it. Now, next step is to get rid of the I loop. Okay, so let's edit the code. So to get rid of the that, what I will do is how we can do that. Yeah, it will be that each thread will do a for loop of will do the J loop. Fine. So what I will oops, comment this here, because what I want to do is will be how can I do this? So let's say int e equal so I get I think that this should work. Also, let me check that because the size if we have threads 256, the threads per block. Also, the matrix is because I'm iterating by the number of rows, so will be four blocks. Let me check in the when I execute. Also, you see here that this is like a more elegant way to define the number of logs in the x-axis and the y-axis. So the number of blocks here will be, yeah, as a result in 4. But well, the first, the best way is to, yeah, to execute that and see if that that works. So I will execute, I will do make and submit. And probably I'm making a mistake, but well, let's see. So I will check execute minus me. Okay, this is done. Let's learn that one. Since that it works, I get the same number of right. And let me check results stats.csv. So this is the number of nanoseconds that takes this version of the code. Let me go to the performance. Let's say I is that one. So you see that getting rid of one loop, I get the time is much faster than when I perform that in a serial. Next step is eliminate the J loop and have a parallelism over both rows and columns. For that, I will need to specify a J, and so each thread will have will execute one element of each thread will execute one element of the matrix, rather than doing a loop. Okay, so let's see if I edit the file again. We are here. Actually, what I will do here, I need to do several changes. I need to change the kernel. Actually, I will rename this with the yeah. And I write int j equal log dx dot y multiplied by log dim dot y plus d dot y. I will get rid of this for ACT. Get rid of this. And actually here, I need to get rid of this as well. And I will execute, so each thread will perform that operation there. What I need here to be careful is because when I launch the kernel, this kernel is a 2D version, so I will need to go to the kernel launch and be careful of how things are. I will comment it here because I will need to do these changes. So int mblock x will be 1 plus mrow minus 1 divided by threads per block. Oops, sorry. 2D. And now you int m blocks y will be 1 plus n column minus 1 divided by the threads. If I manage to write correctly, per block 2D. Also, thread per block will be 2D, and here, yes, per block 2D. So here, rather than having blocks in one dimension, what I will have is a subset of blocks in 2 dimensions. So in on the x-axis and the y-axis, and also the number of the threads per block. Actually, here I made a typo. If we go to the code, you see that the definition here is threads per block in 1D is 256, but threads per block in 2D is 16, because it's 16 multiplied by 16. Yeah, seems okay. There is a question in the chat about the formula. Yeah, maybe I made a mistake with the. Yeah, give me a moment. Actually, let me find the formula. Yeah, it's here. What we are. Why is it that you use the ISA is divided by the number of yeah, okay. So the number of rows, for instance, if we hmm. Yeah, that okay. That yeah, that doesn't sound the best way. So we'll execute that, but what we'll do is we'll um, okay. That let's execute this and have a look. Okay, that's a fair question. Sorry, I'm using VI, and sometimes it could be a bit tricky to. Okay, so one. Yeah, let's execute that. I'm confused because I think the we'll see. Right, let's do make. Well, using the and let's execute with yeah, we have to submit. Reminds me what we're going into. Okay, this is the ready done. We last one was this one, 92. Okay, so we are getting the number of logs for X is 62 and the number of logs is 32. Okay, now I'm also a bit confused. Let me. Okay, the assumption that, but yeah, this has been a while. Well, the result is correct. Okay, I will go to the question now in a moment. Let's check the performance of the result stats CV. So this is the time that we get. I will copy that in the file. I will call it JLoop. And here you can see that when we use, when we delete the loops on each on the, for each of the, the I loop and the J loop, when both of them are deleted and we create as many threads as elements are in the matrix, the performance is much better. But what if is this and also there is a question in the if the coalescence is right or not. So what what we'll do is in the code, I will double check now on in the break, but the question that this is like I believe I need to, but this that the order of execution is 1 plus this. So first this is done, and later this is done. But I need to double check that because maybe it's not. Yeah, now I'm a bit confused as well, but I double check all the data. But yeah, that could be. Yeah, I will. What I will do on the break, I will write a small sample and see if that. But yeah, we'll revisit that in the. We'll revisit that after the break. And this is a fair comment that James made. This is also made in case that because well here we're not cheating, but the number of rows, columns are chosen according to the size of the vector. That is. So we have the matrix, the number of rows is 1024, 512, the number of columns, and we have threads per block, 256 and 16. But it could be the case that the number of rows is bigger, or the number of columns is bigger, so we will need more blocks than. And here one thing that I'm not, I should do is to include a if loop to avoid that access to positions of memory that doesn't exist. For simplicity, I will delete this. And what I will do here is I will just to I will copy these lines here. And what I will do is I will swap the indices here. And check if I get an improvement with the coalescence memory. Compile, make. Oops, there is an error. There is I think I brought something here that is not. Yeah. I will execute, start to submit. Last one must be this one. Let me check if the result is correct. Oops. Yeah, here I made, because I swapped the indices, but yeah, I forgot to do something. Let me see what I forgot to do. Okay, yeah, that's the something that I forgot to. The right one will be AI multiplied by n column plus j. Will be equal the same AI multiplied by n column plus j, and then the rest will be the same, plus alpha, if I manage to get alpha, multiplied by x I multiplied by y j. Oh no, is the same? Is this similar? No, what I just changed is the no, this is wrong. Yeah, something is wrong in the execution. Okay, what we will do is because now I'm aware that we are in the on the break time, we will have a 15-minute break, and we'll continue with this, and also we will learn about managed memory. I will during the break I will check what is going wrong with the code. Okay, let me see where we are. So yeah, we will have a 15-minute break. I will put the timer to yeah, this. We'll have actually let me have this. Okay, so we have a break until 10 past 11, and yeah, after that we will see the solution to this the last step of the exercise, and go through the managed memory lesson. Yeah, see you in 16 minutes. Okay, hope you have a nice break. Let's finish the exercise and continue with the managed memory. Let's open the so the error of the exercise was not here. Here was done correctly. The thing is when we modify this when we modify the indices, we need to bear in mind we have swapped I by j. Oh, sorry. Yeah, today is not my day. Application is, yeah. Thank you. So this is correct, but here, if you see, we have swapped the indices. When we do that, we need to bear in mind the number of blocks that I launch. So here, if you notice, I have swapped. So before this was X, Y. So I need to, because I'm using I'm swapping the indices, so I need to swap this as well. So I will need to do this, and in that case, it will work. So this was the mistake I was getting before. So if I execute the software, and you see that the elements now are correct, and according to the results, since that when I swap, I mean, we were already executing the memory coalescence version. If I swap the indices, see that the second version is the performance is 16,000 rather than 15. So we were already executing the right one. Also answering the question about because we are okay. Give me a exercise about this. Here we are performing the order of the this will be like 1 plus 1024 minus 1 divided by 16. So the order that is performed is first is the operation that is on the parentheses in the on brackets. So this will be 123. Actually, I can get rid of this divided by 16. Here I'm performing an integer operation. So what I will get here is 1 plus 15. I mean, will not be an integer, will be like a 15.94. But because it's an integer division, I'm getting rid of I truncate and get rid of the decimal part, and it's a 15. So the end result will be 16. And as it was said, normally we use one block more in case that for some reason we don't get the we have more elements that we will need an extra block in case that we don't have like an exact let's see the number of elements in the array and the number of elements in the block is not perfect. So this is the order of the. I will not save this. Do you have any questions in the? No. I need to do. Okay. I see there is a comment in the chat about using a heap on jacks. I will have a look at that, but yeah, that. Because, okay, I see that question in the chat that is why is it because there we are performing an integer division. Integer division means that we don't, if we get rid of the decimal part, the result will be this. I will copy that in the chat. So we will get this, but because we don't care of we only take into account the 15. We don't get into account the rest. Because if you notice on the code, m row is an integer. If it was like for instance something like a float n row, the result will be different. Also a way to force if we want a floating point. I mean, you can do a floating point division, but if you notice the m block x was here is an integer, so this is an integer, so everything is performed on also even if the division is like a double or float, because we are saving on an integer, we are losing the decimal part, if that makes sense. Is that no? Oh, sorry. Yeah, you're right. I was. Yeah, I was dividing by. Yeah, okay. Yeah, the result is because I was doing 60. Yeah, the number. No, you're right. The number, if I was dividing by 64, that was my mistake. Yeah, I was. You're correct. It's I was dividing by 64 rather than. Sorry, that was my. I should get another coffee. Okay. So, any other questions before we move on? If not, I'll share the slides. Mm, So I guess you can see my slides of managed memory. So okay, so far what we have done is we have worked with explicit memory allocation. What that means is we have two pointers, one pointer to the host memory and the one pointer to the device memory. When we work with the C++, we use malloc, and when we work with the, for host, we use malloc, and for the device, we use heap malloc, because we are allocating memory on the device rather than on the host. And then when we run the kernel, I use the device pointer. Yeah, this is what we have done so far. Yeah, but it said here that we will need, to have, because we are using a explicit memory allocation, we will need both to keep both pointers. There is a solution that I will do a bit of a spoiler, that usually performance is not that as good, that is a user managed memory. So when we execute a software on the GPU, behind the scenes, there is an API that when we do the allocations and answers, etc., we have done everything in let's say, in an explicit way. But we can delegate that memory transfer to the API, and that will handle the memory transfer. In the case that we use managed memory, we would need only one reference, one pointer, and it will simplify things. You notice there that rather than having a host pointer and a device pointer, I will have a pointer, and rather than calling doing like let's say allocating a memory on the host and allocating memory on the device, I will do a heap malloc manage. And the code will be, let's say, easier, will be simplified. To the memory that we allocate with the heap malloc manage is released as well with using the same using heap free. We will not need to use another function. What is advised here, but well, is that for instance, if you want to do let's say something quick, first you use managed memory, and to get a better performance, you move to explicit malloc, heap malloc. but it's bit up to the developer, if because some of them they could be quite comfortable already with explicit memory allocations. So let's say doing managed memory and then explicit memory could be like a double work, but that will depend on the let's see the developer. But yeah, this is like one approach that at first you tackle to solve to create the parallel version with the managed memory, and then you move to explicit. And actually, you can also compare performance of both versions. So here, managed memory is not how to say. You will see that the code will be simplified, but it's not like the best solution, because behind the scenes you will still need to do the memory transfer between host and device to host, and this is done behind the scenes with what is called page migration. That when a memory is needed on, like from a piece of data is needed on the device, and that piece of data lives on the host memory, you will need to do the transfer and do the operation. So this will, yeah, when you access that piece of data, you will get a page fault, and this will need to be migrated copy from host to the GPU before the kernel can continue. So the kernel execution will stop until the memory is available. And the other way around, if you do the same if you do the same in the piece of data that you get access on the host is on the device, it will need to be transferred as well. So to avoid this, let's say, page fault, you can execute before the kernel heap mem prefetch async is the, so you can do some prefetching. Using that function is what you do is an asynchronous call, and what you is you provide a hint to the API and tell, look, this memory will be used by the GPU, and if everything works okay, that hint will move the memory from copy the memory from host to device. Also, you can advise the heap runtime regarding memory access patterns. So you have 4 options. So you have a heap mem advice set read mostly, in case that the data will be only like let's say read based and occasionally written. The preferred location, if which device will be, or if it will be CPU or a device. What device will access the memory, and also the operations that if it will be coarse grain or fine grain. So you have like these 4 options on the when you call heap mem advice. So you have two options. You can set heap megabytes set read mostly or unset read mostly. You can find further information on the heap documentation. Okay, so now we have the exercise that we'll do the exercise until the lunch break. That will be at noon. The exercise is we will get the previous code that we have developed, and we will modify that code, and we will use managed memory rather than explicit memory. Once that we do that, we will run the code with the profiler, and we will check if the solution is faster or is slower. Also, you can play with the prefetching and see if that makes any difference. And that's the exercise. If you have any questions in the meantime, please let me know. I'll give you half an hour to complete this exercise, and after lunch we will see the solution. Okay, so we are now on the lunch break. So have a nice break, and see you at 1 p.m.